title of my talk is Information Learning and Incentive Design for Societal Networks. Today's societal systems are rapidly embracing an exciting era of digitalization. And at the center of digitalization are the technologies and platforms. These technologies and platforms are able to provide recommendations and services to a large number of human users, as well as the operators of the societal systems, and to consume the facilities of the infrastructure. These technologies and platforms are made possible thanks to the rich source of data that is collected both from the human users as well as the sensors embedded in the infrastructure facilities. Well, despite the advanced technology capabilities, things are not always bright. So here are some examples. Well, in fact, there are lots of protests, not just in LA, but also in Bay Area as well as in Boston, that calling for the Google Map and Apple Map to stop routing so many travelers into the short neighborhood, because they really send too much traffic to these small areas during the morning rush hours. On the other hand, study also showed that Uber and Lyft finally admitted that they are actually making the traffic worse, especially in the mega cities, due to the fact that too many people shift from public transportation systems to use these ride-hailing services. The reason is that these new technologies and services can in fact sometimes worsen the misalignment of individual incentives and the societal welfare. Moreover, although autonomous driving technologies can potentially free us from driving in the future, it may not free us from congestion. And one professor, Professor John Walker from Berkeley CEE, actually showed by a very smart experiment that robotaxi may increase the total miles traveled by over 83%, which is a very large number, and congestion can get much worse. The reason here is that the technologies of autonomous driving is still subject to the constraints of the physical infrastructure capacity. Not to mention that we need to keep in mind that increasingly deployed sensing and control units in infrastructure that support these platforms can potentially make our systems very vulnerable to various random and adversarial disruptions. Well, these real-world issues really bring forth the importance of answering the following design question. That is, what is the impact of these technologies on today's societal systems, how they affect the strategic interactions of their human users and system operators, as well as how can we leverage these technologies to really design the system in order to improve the societal outcome. To answer these questions, it's very important to notice that the outcome of societal systems are governed by both the aggregate strategic interactions of their users and system operators, as well as governed by the physical constraints and the stochastic dynamics of the networked infrastructure. Well, classical economic theory or engineering system theory often emphasizes one aspect, but less on the other. The main message that I want to convey here is that it really needs to build a framework that accounts for both the human behavior and institutions, as well as the dynamics and stochasticity of the engineering systems. And the research objective, so my own research objective is to build such a framework. And here I take the inspiration from game theory, mechanism design, machine learning, optimization, and control in order to build new models and new design guidelines. My time is limited, but I will try to briefly convince you that this is a good approach of solving the design problem by some of my work. The first part is the value of information and information design. So people are more and more relying on these navigation apps to make routing decisions. And due to the technology differences, these navigation apps, for example, here, the Google Map and Apple Map can actually show different route recommendations to their users. And this actually creates the information heterogeneity experienced by the users of different platforms and can result in different realized and experienced travel time. Well, people will assess and compare different apps, and then this will result in their choice of information platforms, and this leads to the equilibrium market share of these platforms. The question we want to ask here is, how does this heterogeneous information environment affects the traveler's choices and the congestion, and how can we assess the relative value of information for different users? So I want to convey the intuition of this problem through a very simple example. So we have two routes in a network. So it's a two-route parallel network. One is the highway that may or may not have an incident. When there is an incident, then the cost of the highway will become higher, but otherwise in nominal state, the highway is much shorter than the detour. So a group of people who use information platform knows exactly whether there is an incident, while the rest of the people have no information of the incident. The scenario one is that this information of incident is only shared by a small size of the population. What happens here is that when there is no incident, the people who have this accurate information will choose to take the highway exclusively, while the rest of the people, since they do not know, and because of their large size and to avoid congestion, some of them will take highway while the others will take detour. However, when there is actually an incident and the informed population knows about it, they are going to switch to exclusively take the detour. This allows the informed population to exclusively avoid running into incident, and they actually experience lower cost than the other population. So in this case, information has positive value. On the other hand, when information is shared by a lot of people, so the size of the informed population is very large, the informed population can no longer exclusively take the highway because of its large size and the congestion imposed by people who receive the same information. As a result, both populations will split on both routes in both states, incident or nominal, and they actually experience the same cost due to the congestion. So in this case, information has zero value. What I did in this work is basically to build a general Bayesian congestion game framework to analyze the impact of multiple information platforms, which have heterogeneous accuracy levels of their signals and can be potentially correlated to assess how the joint distribution of the signal as the asymmetric information environment on the routing behavior, the selfish routing behavior and the congestion. So here the selfish interaction is modeled as the Bayesian Wardrop equilibrium of this game. Well, we have three contributions. The first is the complete characterization of the Bayesian Wardrop equilibrium for this general network environment and information environment. The second is that we identify three regimes as the changes between the using population sizes of any pair of information platforms and assess how the relative value of information can be positive, zero, or negative. So this reveals the trade-off between the gain from having this information versus the congestion externality imposed by people in the same population. The third is, based on the analysis of relative value of information, we analyzed when people are able to choose which platform they want to use, what will be their choice of information and the resulting equilibrium market share of these platforms. Well, building on these results, we can go one step further to study how to design the information environment in order to reduce the overflow of traffic in small residential area. And because of our analysis of the relative value of information and the choice of information platform, this allows us to be different from the classical Bayesian persuasion literature in a sense that we allow the travelers to decide if they want to opt in of receiving the signals versus opting out. And in fact, even with this flexibility, we show that the optimal information design can minimize the traffic overflow and without sending the signals to all of the people. Well, in the second part on multi-agent learning, I go beyond the static setting and try to really close the loop. So the first part, we studied how the information is affecting the strategic interaction and the outcome in the network, the system. The second part, I close the loop to study the case when there is repeated interaction between the platform and the players, in the sense that the data that is used to estimate the parameter is generated as the outcome of this strategic game. And this leads to the dynamic interplay between learning of the unknown parameter on the platform side and learning in games with imperfect information. And there is a repeated interplay between the two. So this leads to the non-IID data set that is endogenously generated by the player's strategies. And I developed new tools to study this dynamic interplay between the statistical learning and strategy learning of the game. The theoretical results we showed includes the convergence of both the parameter estimates and strategies, stability properties in terms of the local and global stability, as well as under what condition this will converge to complete learning. Well, the application of these theoretical tools is to design adaptive tolling mechanism. So this is one application that induces socially optimal outcome in networks with unknown latency function. And what I'm currently working on in Berkeley is to really extend this approach and to study the adaptive mechanism design in dynamic environments. Well, I don't have much time left, so I will just quickly mention the third part of the work is the incentive design in networks. So recall that I mentioned the autonomous driving can potentially jam-pack the roads, but I believe that the key here is to design the correct incentive mechanism to incentivize travelers to efficiently share the limited capacity of the network. So I proposed a market design approach to incentivize this efficient carpooling in the traffic network. The challenge here is that we need to account for both the network topology of these transportation systems, as well as the integer constraints. Well, I take inspiration from the theory of both combinatorial auction and the theory of network flow problems, and developed a polynomial time algorithm for computing the equilibrium of this market mechanism. This is a brief summary. I studied the value of information and information design in routing in general network. This is the game theoretic analysis on the trade-off between information and congestion. I also studied the multi-agent learning with adaptive strategies that focuses on bridging the interplay between statistical learning and strategy learning. And this leads to the learning for tolling design. The third is the incentive design that focuses on the computation of market mechanism and the network and integer constraints. So all these three aspects fall in the framework that I presented at the beginning, which is at the intercept of game theory, mechanism design, and engineering systems. Thank you. I can take questions.
Questions for Manxi? Let's thank all the speakers again. So the next session will start at 11:20.